All right. Let's see. Okay, so we're going to find all the information that we would from a curve sketching problem. Relative max, relative min, increase, decrease, concave up, concave down. Okay. Start off with f prime. X becomes 1. Cosine x becomes negative sine x. So okay, set f prime equal to 0. Solve for sine x, so I get 2 sine x equals 1. Okay, sine x equals 1/2. Okay, so think about unit circle values. Where sine equal to 1/2, sine is equal to 1/2 variations of pi over 6. So normally we would say pi over 6 and 5 pi over 6. Okay, both of these are within the interval, but notice it's going all the way to negative pi. So we also need to include negative pi over 6, negative 5 pi over 6. I'm sorry, negative 5 pi over 6 is going to be negative. Okay, so that's positive. Let's see. Yeah, if I add and subtract 2 pi from this, let's see if it will land inside the interval. So if I subtract 2 pi, this will give me negative 11 pi over 6. That is more than negative pi. That's further out than negative pi. Okay, so that's not going to work. If I subtract 12 pi over 6, I get negative 7 pi over 6, and that's also past the interval. Okay, so we can always test to see whether we're inside the interval by adding and subtracting 2 pi, because we just want to know whether there's anything in this interval that will allow for, yes?
Wait, why are we subtracting 12?
Sorry, so we're subtracting 2 pi, but I'm just matching the denominator, so I can add and subtract, with common denominators. But yeah, looks like our values are slightly outside our interval, so we're not gonna, we tested them out, but it's not gonna quite fit inside our interval. Okay, so we're going to create our sine line. pi over 6. Okay, we want to choose values in each subinterval to test against the derivative function. So between negative pi and pi over 6, I can choose, anytime I can take advantage of 0, I'm going to take advantage of 0. Between pi over 6 and 5 pi over 6, I have pi over 2. And I know it's hard to find pi over 6, the special angle between pi over 6 and pi, but the graph is just going to oscillate. Okay, so we know we can kind of predict what's going to happen based off of the previous, yes.
If we know the graph is going to oscillate, we can just solve for one of them. Like only 0 and not even do pi over 2 because we know it's going to be opposite.
I want you to try. I want you to try. I understand if you can't find something, but I want you to just show me that you're making the attempt to test each interval. Okay. Yeah, I know this is tough here without a calculator, but anything that you can test, I want you to test. Okay, so we'll test 0 into derivative. F prime is 0. I get 1 minus 2 sine of 0. So that's a negative. I'm sorry, 2 sine of 0 is going to be 0, so that's a positive. Graph is increasing. From pi over 6, we're going to test pi over 2. Sine of pi over 2 is 1. 1 times negative 2 is negative 2. 1 minus 2 is negative. Again, we know it's tough to find something between pi over 6 and pi. The graph will oscillate. Okay, we'll come back and find locations of these critical points. Okay, but right now we have an idea that there's a relative what? Max, relative min, and increase, decrease, increase. Okay, so we're making progress. Let's move on to second derivative. F double prime, 1 goes away. Sine x becomes cosine x, but the negative stays. Set the second derivative equal to 0. Okay, so we're asking ourselves, where is cosine equal to 0? X equals what? Pi over 2, right? 3 pi over 2. But it looks like 3 pi over 2 is outside the interval. But what about negative pi over 2? What about negative 3 pi over 2? So these are just subtracting 2 pi from my original values just to see if it's going to land inside my interval from negative pi to pi. And if we think about our second derivative sine line here, right, we know that 1/2 is going to land nicely in between. You know, negative 1/2 is also going to land between, but negative 1.5 is going to be too far out, right? Okay, are we okay with those critical points? Yeah.
Technically speaking, I understand you want to see that, but will this graph also oscillate?
Yes.
Okay.
Mm-hmm. Okay, so let's test values here between negative pi and negative pi over 2. So I have negative 1/2. I have -1. What's between -1/2 and -1? -3/4. Between -1/2 and 1/2, I have 0. Between 1/2 and 1, I have 3/4. Okay, we're going to take these values and test it against the second derivative function. Now, if you don't know what -3 pi/4 is, you can always add 2 pi to make it something that looks more familiar to you on a unit circle. So if I add 2 pi, or in other words, add 8 pi/4, I get 5 pi/4. So these are the same things. All right, so if you don't recognize an angle, add 2 pi or subtract 2 pi, and then you'll get something that will be equivalent. Okay, so cosine in the third quadrant, right? What's cosine in the third quadrant? Positive or negative? Negative. Negative times negative is positive, right? So we know that this interval is going to show concave up. Okay. Plug 0 in. 0 in for x. Cosine of 0 is 1. 1 times -2 is negative. Concave down. Okay. 3 pi/4. Cosine of 3 pi/4. You know that's going to be negative, right? Cosine in the second quadrant is negative. Negative times negative is positive. Okay, so we've gathered a lot of information. The hard part, well, the majority of the hard part is done. You know how the graph is going to move. You know that there's relative max, relative min. You know there's points of inflection. So now we're just going to gather all the order pairs from the original function. Okay, so I'm going to put this on a separate sheet just so I can. Okay, any questions so far? Are we good? Finding the derivative, finding critical points, testing each interval. Okay. All right, so now back to the original function. Now I'm just going to gather information so that I can have some points to graph. So I need to find locations of the endpoints. I need to find locations of the relative max, relative min. I need to find locations of the POI. All into the original function now. And right, when you're graphing, you're just doing ballpark values. Okay, so if you realize that pi is a decimal, just find the closest whole number, right? Because we're not concerned about super accuracy, right? As long as you have some ballpark values, that's really what I'm looking for. Okay, so cosine of negative pi, we know that same thing as cosine of pi, which is -1. -1 times 2 is -2. -2 minus 3, around -5, right? So if you can just ballpark your values, if you see pi, just pretend like it's 3 or -3. Good with that? Okay. F of pi. This is 3 minus 2. Right? Cosine of pi is -1. -1 times 2 is -2. 3 minus 2 is 1. Okay. We also want to test pi over 6, find locations of pi over 6. So think of pi over 6 as 3 over 6, right? Think of that as 1/2. Cosine of pi over 6 is what? It's cosine of pi over 6. That's cosine pi over 3 is 1/2. So cosine pi over 6 is root 3 over 2. Okay, 2's cancel out. We're left with root 3. Now, if root 3 or root 2 shows up on the test, I'll give you a guide. I'll say that root 3 is around 1.7. Okay, and then root 2 is around 1.2. Okay, so 0.5 plus 0.7. Okay, ballpark values. Okay, f of 5 pi over 6. Okay, 15, this is 5 times 3, 15 divided by 6. It's around 2.3 or something, 2.5, right? So you just make a rough estimation, and that's good enough. Okay. Cosine of 5 pi over 6. This is going to be similar to pi over 6, except it's going to be negative. So 2.5 minus 1.7. So 0.8. Okay, one more. Two more. F of negative pi over 2 and pi over 2. Now, these may not be as necessary because you know your graph is going to fall along the path. You know your points will fall along the path of the graph. Okay, so it's not as important to find these ordered pairs. It just kind of helps. This is going to be 0. Okay, so we have a bunch of these anchor points to help us with our sketch. Okay, so here's our graph. So we're starting all the way over at negative pi and extending out to pi. And then along the way, we're going to have some critical points here. So we have negative pi over 2 that's going to show up. We're going to have pi over 6 that's going to pi over 6 is positive now. It's the only value in the negative here. Okay, negative pi is going to be all the way down to negative 5. Negative pi over 2 is going to be a negative 1.5. Pi over 6 is going to be at 1.2. Pi over 2. .8. Pi over 2. Oh, I messed up here. So I said root 3 is 0.7, is 1.7. My bad. This is going to be at 2.2. Yeah, because we want a relative max, so this should be the highest point. Okay, and then pi back at 1. Okay, so if we just sketch the graph just based off of the slope sine line, it should match with the slope what we expect, right? The graph is going to be increasing up until pi over 6, decreasing until pi over 6, and increasing again, right? So we kind of have an idea how the graph's going to look. Very good there. So yeah, so I made a mistake with ordered pairs, but I was able to catch myself because I realized, wait, this should be a max, that should be a min. And yeah, so I made a mistake there, 1.7 instead of 0.7. All right, so we have an idea how our graph's going to move, and then we know our points of inflection is going to be where the curvature is going to change. So we're going to start off with concave up, changes to concave down, and then back to concave up. You can write out all the intervals of increase, decrease, relative max, relative min, POI, just based off of the sine line, right? And if I ask you for absolute max and absolute min, just pinpoint those values from what you can gather, right? So make your best estimation. You know that pi over 6 is going to be your max, so 2.2. Absolute minimum is going to be your starting point there, so -5. All right, so absolute max, absolute min, you just look at the graph and make your determination there. Yeah.
Test when you provided a graph or when you have us sketch it, like kind of here, or like when you give us a hint.
Yeah, you're just going to freehand it.
Okay.
Okay. Again, you know, the accuracy is not super important. I just want to know that you can take this information and just that you can create something to show me that that you can maneuver through this, right? So I'm not going to look at this saying, oh wait, that's not quite 2.2, right? That's not the purpose, right? If you can ballpark values and you can kind of work your way through, that's more important to me. It's a big problem, but you know, we're really kind of taking our curve sketching knowledge and just putting it all together here. Okay, let's do some random problems here. Do you have any preference? So curve sketching is the big one there. You'll see an inverse trig derivative. You'll see an implicit differentiation. You'll see a particle motion, related rates, mean value theorem. All right, so I'm just going to pick having us do, let's do inverse trig and an implicit, okay? So let's find the derivative for this function. Okay, so what's needed here if we want to find the derivative? Okay, product rule, good. Definitely product rule there. We also need knowledge of some other rules, right? What do you know about our cosine? It's related to what? It's a negative version of what? Arc sine, yeah. So remember the chart, the table that we went through. You know that your numerator is always going to be u prime. And if you go through the whole process, you know that arc sine has a square root. Arc secant has the u squared that comes first because the u's are next to each other. So this is going to be 1 minus u squared. And then we also need to know what e to the u is, right? What's e to the u? What's the derivative rule? E to the u times u prime. Okay, so try that. Go through. Hey, what's negative u prime going to be? A negative of a negative 2x, right? Which will be positive. Square root of 1 minus u squared. Okay, so that completes product rule. Now I can move on to this rule here. Minus e to the u times u prime. Not a whole lot of cleanup I'm going to do, just see if I can push some things together. Okay, any questions with 2?
What kind of problem is that?
Oh, number 2? Number 2 is problem involving arc trig. Yeah, so inverse trig derivative. This is like, this will be a problem that you can expect involving inverse trig. Okay, what do you see is needed for number 3 here? Mm-hmm. Mm-hmm. There you go. And also just derivative, right? A trig derivative. Try that for y. Okay, what's cotangent's derivative? Mm-hmm. But negative, right?
Yeah.
Okay. Okay, so negative cosecant squared u times u prime. When we get down to u prime, 2y's derivative becomes 2 dy dx. So there's a lot going on here with g prime. Any questions there? Okay, and these are all just singular terms. What does y turn into? Good, just 1 dy dx. And I like to put a 1 here because that's a reminder that when you factor a dy dx out, there's still a 1 left over, right? So it's I think it's helpful having that 1 there. Otherwise, we may forget and just completely lose that term. And the 4 becomes what? 0, right? Goes away. So now I'm just going to rearrange. I have 1, 2, 3, 4 terms. I want these 3 terms together so I can factor dy dx out. So this f prime g can all be merged into, it's all one term, right? I'm just trying to clean things up here, putting all the coefficient and variables in front of the trig. Okay, divide over. Yeah.
Why is there 4?
Oh, sorry. No, you're right. Yeah, I saw that too, and that 2 is inside that trig. And I also put the y there, so I shouldn't have done that. This should not be touched. It's just going to be the 2 and the y squared. Thanks. Yeah, this 2y is not a coefficient that we can merge. minus 2y squared. Okay, is that what you guys got? Okay, so in class, I'll do particle motion, maybe revisit a mean valley theorem, and do another related rates. Well, actually, we'll do a curve sketching class as well. Okay, and then tomorrow morning, I'll just pick out maybe curve sketch, related rates, and particle motion for us to do tomorrow morning. Okay. All right. Thanks, everyone.
Hey, Mr. Yang.